Hi, it's time for another math easy solution. Today I'm going to go over a laboratory project and look at an elusive limit. And again, laboratory projects are just interesting projects at the end of several sections of my calculus book. In this case, it's going to be on series, so very interesting stuff. So again, note as always, if you don't have time to watch this whole video, you could play this at a faster speed. You can also download, read the notes, or view the notes on the Hive blockchain and article format. Or you can watch it in parts. The link to all the, the link to everything is going to be in the description below, including the parts. It has timestamps for each part that you, of the video, so that you can skip to whichever ones you want to. Anyways, let's jump right in. So calculus book reference. Note that I mainly follow along the following calculus book, and this is going to be Calculus Early Transcendental 6th edition by James Stewart. And note that, quote, laboratory projects, again, are interesting math projects at the end of several sections in my calculus book. Yeah, and in this case it is at the end of, it is at the end of the section on Taylor and Maclaurin Series, which again are just a power series. So let's jump right into topics to cover. So laboratory project, an elusive limit. There's going to be 6 questions. And then look at the solutions to 1, 2, 3, 4, 5, and 6. So I just put these all in the topics to cover so that I could put timestamps for each one, including the topics to cover, so you can even skip through all the introduction that I usually do. So anyways, let's just jump right in. So laboratory project, an elusive limit. So this project deals with a function, and I'm going to write this as f of x. This equals to sine of tan of x minus tan of sine of x. Divide this by, now we're going to look at arc, or inverse sine of x. Yeah, inverse sine of x, this is going to be like this, and then of the inside is going to be arc of the tan. So it's going to be exact same as the top, but then at the bottom. And I'm writing this as arc just because the calculus book has it written like this, and I'll just write it in the inverse form that I prefer in a bit. So this is going to be tan of x like that, minus arc tan. So now it's the exact same as the top, but now you're just doing the arc of it. This is going to be arc sine. Oops, this is going to be r sine of x, like that. And here it's moved it in the center, and yeah, let's just write it in the usual format, or the format with the -1 terminology. So the top's going to be the same, sine of tan of x minus tan of sine of x. And then I'll divide this by, now you're going to have the inverse sine of the inverse tan of x. So just write it like that with the power -1 like that. It just means it's the inverse. Now it's going to be inverse tan, and then inverse sine inside of x, like that. And let's just bold this one, just because, or box this out, just because I'm used to this one. Alright, so now that we have this equation, so now the questions that we're going to look at are going to be over here. So question 1, use your computer algebra system, CAS, or CAS, just abbreviation, to evaluate f of x for x equals 1, 0.1, 0.01, 0.001, and 0.0001, so 3 zeros. And then the question asks, does it appear that f has a limit as x approaches 0? And then we're going to look at these questions. I'll read those ones later as we get to each question. So let's just go over question 1. Scroll down here. So solution to question 1. So the calculus book solution manually states it used the Maple Mathematics, or CAS software program, which has 10 digits of precision, to calculate the following table of values for f of x. So if you plug in f of x there, this is from the calculus book solution manual. Yeah, message me and I'll send it to you. I don't want to put a link out just for legal / copyright issues. Anyways, so if we plug in, so we plug in 1 inside here and then see what we get for f of x. So let's just go over that, then we'll go over question 2 and read it out as we go along. So if we have x is 0.1, then f of x is going to get 1.1838, and then if we get 0.1, we get 0.9281, and then if we get 0.01, we get 2. Again, it's from a solution manual, calculus book. And we have 0.001, we get 3.333, and then 0.0001, we get 3.3333. So it looks like it's approaching 3.33, or 10 over 3. So the results of this project will vary depending on the CAS and precision level that you're using in your calculator. In this case, it appears that as x approaches 0 from the right side, that's why we have a plus. So it's from a positive side. So it's going to be positive 1, positive 0.1, etc. all the way there. Then f of x is approaching 10 over 3. And note that f is an even function, and I'll prove that in a bit. Thus, f of x approaches 10 over 3. And again, 10 over 3 is just 3.33. As x approaches 0 from the left side, and thus as x approaches 0 from the either or, so left or right. We can show that f is an even function, that is f of negative x equals to f of x, so it's the same thing on the left side as the negative or the positive side, as follows. First, let's just recall a bunch of stuff, and this is just for reference. So recall that if you have sine inverse y of x, this is the same thing as writing, this is the idea of the inverse. It is the same thing as reversing and writing y equals sine of x. So in other words, inverse is just a function of the inside variable, and then where the outside is the one that's changing. Yeah, so effectively all it is you're just switching the variables. And then also the tan of y equals x, if you have that, is the same thing as writing y equals to tan of x. So effectively all you're literally doing is reversing these, and also recall that if you were to graph these out, yeah, let's graph this out. So this is going to be the sine and its inverse. Yeah, so if you have just like that, this is going to be your sine function. It goes something like that and keeps going on and on. Let's write this as sine. Or actually, we don't need to write that there right now. What we can do now is, I'm just going to put this for reference. So now we can have, let's say we have an x value here, and we have x over there. Then at this point, this is just to recall for sine, this is going to be our sine of x, like that. But then remember, this is an odd function for sine. So now if we take go with the reverse side of it, so if you go exactly here, which is negative x, the exact same value as this, with absolute value, we're going to get exactly this one, which is over here. This is going to be negative sine of x. So it's an odd function. Everything's going to be odd functions, but eventually, when you put them all together, it's going to be even. And now, if you were drawing the inverse, remember the inverse is going to be mirrored across the y equals x line, and in fact looks like this. It's going to look something like this, where it ends up at pi over 2. And I'm just going to draw it like that. So the inverse goes like that. So again, just recall your inverse function. It looks something like that, where it ends up at over here pi over 2. And yeah, this is all the way to pi over 2. And here, just move that over. This is going to be at pi over 2, like that. And again, the reason is so that we have a one-to-one function. And at this point, it's going to be our pi over 2. For the other side, it's going to be at pi over 2. Anyways, this is for reference. So this graph just goes like this. It doesn't go back in. Otherwise, we're going to have multiple values of y for each x value. Alright, so anyways, now that we have that, so at this x value, we're going to have over here is going to be a negative. It's going to be positive. This is just inverse sine of x. Just to illustrate the difference between inverse sine and sine of x. And then over here at this side, it's also going to be an odd function. It's going to be negative sine of x. Well, actually, it's written over here. So put those dashed lines for the pi over 2, and put this over here as negative sine of inverse sine of x. So in other words, what we have is again, just recall that if we have sine of, and this is going to be a negative sine of x. This just equals to negative sine of x. And also, inverse sine of x. Inverse sine of negative x equals to negative inverse sine of x. Like that. So in other words, these are both odd functions. Odd. And then likewise, we'll show that the inverse tan and tan are the exact same as well. So likewise, if we have, let's just recall the graph of tan. So recall the graph of tan looks something like this. It's going to go like that. This is y. This is x. This is dot, 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 dot. Goes all the way up there. And this is at pi over 2. And yeah, it keeps repeating on the right side as well, but we're just going to ignore that. And yeah, let's say we have a value here. This is going to be our x. So we're going to have a value all the way across here. This is going to be our tan of x. And then the inverse of this is also odd function. It goes down like that. and this is going to go downwards at negative infinity, and we're only looking at from negative pi over 2 to pi over 2. And yeah, this one, let's make this negative pi over 2, like that. Now I keep going further, so then at this point, if we have negative x, this is going to go all the way down to somewhere across here. Let's make it a bit better, like that. It's going to go all the way across, or make it even a bit nicer, like that. And this is going to be at, this is going to be at negative, tan of x. Alright, so now we have this, and then again for reference, let's draw the inverse. Is going to be the mirrors of it, and recall it's going to look like this. So the mirror, so this is the limit going all the way up to pi over 2. The other one's going to go, for the x side, is going to go at pi over 2. So it's going to go something like that. So this is going to go look something like this. Let's try a bit better. Or more horizontal. Let's try one more time. And then it goes like that. And on this side is going to go like that, where this is going to be our pi over 2. So we just flipped the x and y. It's going to be a pi over 2. And it's going to go dashed line across, like that. And this is going to go dashed line across, like that, etc. This is going to be our negative pi over 2. Other one is positive pi over 2. So it goes like that. And at this x value, we're going to have over here, just to show the relative difference, it's going to be inverse tan of x. And then over here, it's going to be our negative. It's going to be the exact same thing, but mirrored to the negative side. So it's going to be inverse tan of x, like that. I mean inverse, tan of x. Alright, so now that we have this, and this was all just to get that, just to show that again, and it's also for reference for myself, just to get a refresher. So what this also means is that if we have tan of negative x, this is equal to negative tan of x. And if you have inverse tan of negative x, this equals to negative inverse tan of x. But again, this is just for reference, and this is going to mean this is odd. So these are all odd functions, like that. This goes a bit better. Odd. Alright, so those are all odd. This is odd. Yeah, because when you put a negative x inside the function, it gets a negative of the same value. But we're going to show that f of negative x equals to f of x, which is even. So thus, so move over here, just put a line. So it doesn't matter. Just put a thus. We're going to show that f of negative x. We're going to plug that inside. So remember, it's going to be sine tan of negative x. We'll put another negative like that, and put another bracket. I'll just put a box bracket just to show the difference. Then minus, that's the reverse, tan of box sine of negative x, like that. Divide this by, now we have the inverse, so sine, with the negative 1 there, of bracket tan of inverse negative x, bracket minus tan, inverse tan. Put a big bracket. Box bracket. Now we have the sine. So again, tan sine, sine tan. And now we have negative 1. This can be negative x, like that. And yeah, the solutions method didn't go over the proof for why it's even, but I just wanted to do this for reference and algebra fun. So anyways, now we have this, and we know that a negative tan of x, a tan of negative x equals to negative tan of x. So all these are odd functions. So we could replace all of these tan of negative x and inverse tan of negative x, as well as sine of negative x and inverse sine of negative x with their same equivalent but with negatives. So yes, with their positive equivalent but with a negative. So now we have this equals to sine of negative tan of x, and then minus tan of negative sine of x. Remember, they're all odd functions. And then we have inverse sine of negative inverse tan of x minus inverse tan of negative inverse sine of x, like that. And now we can do the exact same thing of these ones. So now we have sine of negative tan of x equals to just, well, sine of, this equals to negative sine. So that the sine is also, remember the sine of this and the tan, we do the exact same thing. Those are all odd functions. So this equals to negative sine of tan of x, of positive tan of x. That's going to be our new x. It's going to be our tan of x. So now plus a negative, and then negative, I'll just put a negative minus, or just put a negative plus. So it's going to be plus tan of sine of x. Divide this by, now we have in negative. Yeah, negative inverse sine of positive inverse tan of x, like that. And now minus, this is going to be a plus now. Yeah, plus inverse tan, negative, like that. And yeah, remove this negative now. It's going to be sine, positive. And yeah, so we have this looks like it's opposite, but we can just multiply top and bottom by -1. And when we do that, this becomes positive, this becomes negative, this becomes positive. Yeah, so this one becomes positive, this becomes negative. And we get exactly our function. So this equals to sine of tan of x minus tan of sine of x. And this is going to be sine, inverse tan, minus inverse tan, inverse sine. And this equals to our f of x. So thus we have f of negative x. Let's put it like in line with this. So thus we have f of negative x equals to f of x. So this is even. And we can box this out. Alright, so another way I went over this one. That was just to show that it's even. So the limit, yeah, it goes to 0. Goes to 10 over 3, or appears to go to 10 over 3 as x approaches 0 from either side, negative or plus. So thus we could just write x approaches 0. And yeah, I went over this this bunch of this algebra and math just because this is the one of the only times I'm running in this video. So now when I do the same calculations using Microsoft Excel, I get the following table of values. So if you have fx equals sine, sine tan minus that, etc. So now if I plug this into this one right here, to Excel, there's a link to it. You can go and download and play around with it. And let's just see what the original one was. We had 1.1838, so that was the benchmark. As long as you get that right, everything else should be. Then you can tell it's calculating somewhat correctly. So we have, if we have x, we plug in this one, we get 1.183831, etc. Then if you plug in 0.1, it gets to 1.01, which is different from our earlier calculation, which is 0.9821 from the Maple cast from the solutions menu. So now if you plug in 0.01, we get 1, 0.001, we get 0, 0.001, we get 0. So note that Excel uses 15 digits of precision. And now if we use the decimals calculator, we get the following. So yeah, all the limits are different. So again, we get, if you plug in this decimals calculator, you could put in fx equals to this. And then there's a link to that one. And then if you plug in f of 1, we get this 1.1838, etc., which is the same as our earlier one. So these two are the same for the Excel. This one's 1.0167. It's also similar. And yeah, 35. And then, but then if you plug in 0.01, we get 989. Whereas this one rounds to 1. Yeah, so that just goes to 1. And then the next one's going to be 0.001, we get 0. And then 0.0001, we get undefined. So it looks like it's undefined there. So note that Decimals uses a dynamic system between 15 and 17 digits of precision. Yeah, so I'm going to write this as proofing at the dictionary. So we can summarize below the different calculations methods. So for Maple, that has 10 digits of precision. fx goes to 10 over 3 as x approaches 0. And Excel, 15 digits of precision, we have fx goes to 0 as x approaches 0. And Maple is 15 to 17 digits of precision. Not Maple, Desmos. 15 to 17 digits of precision, and it goes f of x goes to undefined as x approaches 0. So we got a bunch of different limits. So thus it is not clear if f has a limit or not as x approaches 0. So now let's look at question 2. Let's just scroll up to question 2. So question 2 states, use the cast to graph f near x equals 0. And the question says, does it appear that f has a limit as x approaches 0? So let's go all the way down over here. And yeah, so solution to question 2 is the graph of f near x equals 0 from the solutions manual is shown below. So if we have, this is how it looks like from the solutions manual. It goes to, up and down, so it doesn't look like it has a limit or not. And this is 0.01, it's negative 0.01. And yeah, so the graph is inconclusive about the limit of f as x approaches 0. Likewise, the graph of f using the Desmos calculator is also unclear, so here's the same link. And this is what we get. So we get some random stuff like this. This is near 0. So yes, it is unclear. And even when you zoom in, it's all unclear. And yeah, you just go to the browser. So here's the Desmos calculator. So here's the graph. If you zoom in, it just keeps repeating the same thing. So, so it is unclear whether a limit exists or not. You get some random values. So now it just doesn't have any values there. Looks like it stopped calculating a while ago. So you zoom in, you get some random stuff, and it just jumps up and down. So anyways, that is very interesting stuff. Just keep going further. So now, yeah, so it is unclear. So it's also unclear, and yeah, that's question 2. So now let's look at question 3. Scroll up to it. So question 3, it states, try to evaluate limit as x approaches 0 of fx with L'Hopital's rule, and using the cast to find derivatives of the numerator and denominator. What do you discover? And then it says how many applications of L'Hopital's rule are required. So we're going to use L'Hopital's rule to find a limit. So the solution to question 3. So if we take the limit as x approaches 0, yeah, we get the indeterminate form 0 over 0. For example, we just take the limit just to show you. Limit as x approaches 0 of sine of tan of x. Let's put this s a bit better. Of x minus tan of sine of x. Divide this by inverse sine of inverse tan of x minus inverse tan of x and sine, inverse tan of inverse sine of x, like that. And remember that every single one of these is approaching 0. If you look at the graph earlier, just to recall, every single one of these is approaching 0 there. It's all approaching 0 from either side for either inverse or regular function, sine or inverse sine, or tan or inverse tan. So they're all approaching 0 as x is approaching 0. So what we're going to get is this goes to 0, then this goes to 0, so sine of 0. Tan of 0 is going to 0, and then the sine of that 0 is going to 0. So this goes to 0, this goes to 0, 0, 0, 0. And that means the outside is going to 0. So we get a 0 over 0, and this is indeterminate. Or 0 minus. Let's go complete. This goes to a 0 minus 0 over 0 minus 0, which goes to 0 over 0. And this is going to be indeterminate. Like that. Yeah, so it's indeterminate, thus we can apply L'Hopital's rule, reference from my earlier video. So here's a link to it, there's video notes, archive, here's a screenshot from my calculus book, just because it's typed up. So L'Hopital's rule, suppose f and g are differentiable and g prime of x not equal to 0 on an open interval I. Yeah, this is the derivative, g prime of x, that contains a except possibly at a, and suppose that limit as x approaches, as x approaches 0, as x approaches a of f of x equals to 0, and limit as x approaches a of g of x equals 0, or that we have the limits go to plus or minus infinity, or plus or minus infinity on the top or bottom. In other words, we have an indeterminate form of the type 0 over 0, or infinity over infinity. Then the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of the derivatives of f prime of x divided by g prime of x, if the limit on the right side exists or is infinity or negative infinity. And if then if we also have a 0 over 0 on the limits, then we could keep doing that same derivative. Just keep applying L'Hopital's rule. And yeah, let's keep going further. So since the laboratory project asks us to use a cast to solve derivatives of the numerator and denominator, we could use the amazing Wolfram Alpha website. It's pretty epic. The first 6 derivatives all yield a limit of the indeterminate form 0 over 0. Finally, on the 7th application of L'Hopital's rule, we obtain non-zero values. So if you take the 7th derivative, you could just type 7th derivative of sine of sine tan of x minus tan sine of x. Yeah, this is the numerator, sine tan minus tan sine at x equals 0, and it automatically solves it. So this is the 7th derivative, d over dx of 7, but they use this delta symbol, so partial derivative, but anyways, the same thing. There's only one variable. So this is going to be negative 168. And if you do the same thing for the denominator, so 7th derivative of a sine a tan of x minus a tan a sine of x at x equals 0, we get the same thing. Derivative at this, you literally just write it and it will solve it. Negative 168. And we can just illustrate this here. So if we write first derivative of this one, zoom in, of the first derivative, and we just type just one derivative, or first, or or 1/10 derivative, it gets to 0. And if you go to second one, it gets to 0. Solve this one, it gets to 0. Yeah, and there's some graphs that are pretty wild. And then you keep going 3. Let's go for reference just to show you. It's calculating, and it's 0. You go to 4. Calculate and zoom in more, and it's 0. Let's calculate 5, and it's gonna be 0. Let's see how the graphs look. Yeah, the graphs looks pretty cool. The 6th derivative. 6th derivative, it's going to be 0, and there's the graph, looks like that. And then 7th one. Yeah, 7th one, negative 168, and there's the graph like that. Just fascinating stuff. So it goes to negative 168, and again, do the same thing for, this is the numerator. Do the exact same thing for denominator. There's a link, there's archived, and play around with it. You're going to get exactly the same thing, so negative 168. Thus the limit is, and we could take this limit as a limit as x approaches 0 of f of x. This equals to, I'm going to write this as a limit just to save space. I'm going to write the numerator as a function as x approaches 0 of n of x, for n for numerator, divided by d over d of x, which is the denominator. This equals to, and I'll put an h for L'Hopital's rule, and this equals to limit as x approaches 0 of, now it's going to be the the 7th derivative. Put n of x, n7 like that in a bracket for the 7th derivative, and d7 for the 7th derivative of the bottom of x. So the limits equals to the limits, the limit of the n of x over d of x, which is, again, that's just f of x, is equal to the 7th derivative of the top and bottom. And this equals to negative 168 over negative 168, and this equals to 1. They all cancel. So the limit is equal to 1. Fascinating stuff. And so that's the answer. And also note that n of x and d of x are the numerator and denominator of f of x. And I'll just put this comma respectively, so it's in order. So numerator n of x and denominator d of x, like that. Alright, so now look at question 4. So let's just read question 4 right now. So question 4, scroll up. So question 4 states, evaluate limit as x approaches 0 of f(x) by using the cast to find sufficiently many terms in a Taylor series of the numerator and denominator. Yeah, so using the command Taylor and Maclaurin Series in Mathematica, but in our case we'll just use Wolfram Alpha, just because the calculus book is a bit old, and so they probably didn't have access to Wolfram Alpha. And you just throw it in there and it'll just solve it for you. So we're going to basically use the same thing. We're going to find the limit by using Taylor series, or Taylor, Maclaurin, etc. So we're now asked to solve the limit using a cast to determine the Taylor series of the numerator and denominator. So using our trusty Wolfram Alpha calculator, we can determine the Taylor series centered at x equals 0, i.e. the Maclaurin series, for both the numerator and denominator. So we just type in Taylor series of sine tan of x minus tan sine of x. we get this function. So you can just throw that into the wolfram, and we'll throw this one, negative x to the power 7 minus 30, then minus 29x9 divided by 756, etc. Keeps going on. And also there's a plus x to the 14. I'll get to that in a bit. And then if you do this for the denominator, we get Taylor series of a sine. You could just put a sine for arc sine, same thing as inverse, and automatically shows you this. A sine a tan of x, or inverse tan, and then minus inverse tan of inverse sine of x. And then Taylor series expansion at x equals 0, that's just a Maclaurin. We get negative x to the 7 over 30. So it's similar to this one. So negative x divided by negative x to the 7 divided by 30. And then the next one's a bit different. So 29 is 756. The bottoms the denominators are all the same. The tops are different except the first term. And then we get a plus 13x9 divided by 756. And then we have a minus plus minus. This is going to be alternating. There's also going to be a plus x to the 14. Note that O is termed the quote big O notation and used to indicate that the series is a maximum absolute value beyond the evaluated term. So beyond this is going to be maximum of this order. And in our case, x to the 14 indicates that the series sum of the remaining terms is a maximum value at has a maximum value of a constant multiplied by absolute value of x to the power 14. So in other words, that's the order of it. So whatever x is going to be a constant multiplied by whatever this x to the power 14 would be, when x is close to 0 in our case. So yeah, this is basically saying it's going to be maximum of this order, a constant times it by x to the power 14. Learn more, you can learn more at Wikipedia here with big O notation. So I have not covered that earlier, but you don't need this. This is just to show a maximum or limiting factor of the series. So yes, infinite series is going to be at maximum this, and this one's going to be at maximum this one for this type of series that converges. Alright, so thus evaluating the limit of the Taylor series, we have, and I'm going to write this as limit as x approaches 0 of f of x, and then this equals to the limit as x approaches 0 of, again, the numerator n of x over the denominator d of x, and this is going to equal to, in a calculus book or the solution manual used equals to, and then put a CAS just to show that we're skipping through a bunch of work and getting straight to the series. The limit as x approaches 0, and now we have over, and we're going to write the terms that all that matters is actually the first two terms, or the first term is all that matters, but we'll show you why everything else is going to vanish to 0. So negative x to the 7 divided by 30, let's do the first one, negative x to the 7 divided by 30, and minus 29 x9 is 756. So this is going to be negative x to the 7 over 30, or actually better yet, just a bit easier to write, just put 1 over 30 like that, and then x to the 7, and then minus, it's going to be 29 over 756 x to the 9, then it goes not minus dot dot dot, so that's all that matters. And the next one's going to be, remember the first term's the same, negative 1 over 30 x to the 7, and then minus, or this is going to be plus actually because it's alternating. It's going to be plus minus plus minus. So it's going to be 13 over 756 plus 13 over 756. It's going to be x to the 9. Yeah, it's x to the 9. Yeah, 9, 11, then 13, etc. It's going to be, now it's going to be alternating. It's going to be negative plus dot dot dot. And now what I'll do now is I'm just going to multiply this top and bottom as per usual by the highest power, or the first power. I'm just going to do this by the 7 so that it gets rid of it, and then the other one's just going to be, well, x to the 2, and then it goes on and on, x to the 4, x 6, etc. So I'm going to go divide this by x to the 7 so we can cancel the first term, because that's all that matters. 1 over x to the 7, like that. So this means, well, this cancels with this, and those are going to cancel. So it's going to be, pretty obvious. I'll just leave it like that. So this equals to limit as x approaches 0 of, now it's going to be a negative 1 over 30, because the x's, x7's cancel. Now we're going to be 29 over 756. Now we're going to have x to the squared minus dot dot dot. Divide this by, let's move it here to divided by, and then the denominator, this one's also going to cancel, the x7. So 1 over 30, And then this is going to be x. This x7 goes away. It's going to be plus 13 over 756 x squared. It's going to be minus plus dot, or minus plus the next one, plus dot dot dot. It's alternating. And now the later terms are all going to be, well, just 7 power to less, or to the power x to the 7 less. So it's going to be it's going to be 2, 4. So 11 minus 7 is 4, and then 13 is going to be 11. And those are all still going to be have an x value. That's not x to the 0, which is 1. So in other words, when you plug in 0 inside all of these all just vanish. All you're left with is the first term. This one's cancelled, so that's going to be 1 over 30. So then when you plug in the 0 inside here, this all goes to 0. Or not that part, but this part's going to go to 0. This part's going to go to 0. And all the other ones are going to go to 0. Everything else is going to go to 0. This one's all going to go to 0. So all you're left with is negative 1 over 30 over negative 1 over 30. In other words, those cancel. This is equals to 1. Alright, so yeah, that equals to 1, which is the same as our question 3 that we solved using L'Hopital's rule. So this equals to 1. So we know the limit is 1. And now notice what we could do is note that we could have also applied L'Hopital's rule to the Taylor series 7 times to obtain the same result as question 3. So we got to just start from here. So instead of dividing by x to the 7 on both top and bottom, we're going to go, I'm just going to circle this and copy it. And then I'm going to move it here and paste. So let's say we start from here, and then we just take L'Hopital's rule instead of the series, of the power series, as opposed to of the other function using using Wolfram. Yeah, so just copy and paste that there. So now this equals 2, and I'll put a h for the derivative for L'Hopital's rule. So take the derivative of this one, of the top, this is a power rule, just put the 7 down and subtract the power. So this is going to equal to the limit as x approaches 0 of, now we get a negative 7 over 30. And then x6. And the next one's going to be, 29 over 756 times it by 9. Now we have a x to the 8, like that. So you just multiply the top power and then subtract it, dot, 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 and then divide this by. The next one, this is 30. Don't know why that didn't copy. Okay, so now the 7 goes down, so negative 7 over 30, and then x to the 6 minus, I'm just going to be plus 13 times it by, 9, the same thing as before, 756, and then x to the 8, minus plus, dot, 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 and then do this 6 more times, because remember this 6, when you plug in 0 inside, these all go to 0 over 0, so again it goes to 0 over 0, so we do this 6 more times. So do this dot, 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 6 more times. So the next one's going to be the 6 goes down there, and the next one's going to be 5, so 7 times 6 times 5 times 4 times 3. In other words, we get a factorial. So do this 6 more times, and then ultimately we get the last one, which is equals to this is the 7th one. So yeah, the first one plus 6 more is going to be x limit. L'Hopital's h equals 2 for L'Hopital's, like that, x to the 0, and then now we get a 7 factorial, which is again 7 times 6 times 5, etc., divided by 30. X to the x goes away. The next one's going to be number 6 more times, so this goes away. This is going to be x to the 2. This is going to be 29, and this is going to be 9 factorial over 2. This is going to be 9 times 2, 9 times all the way up to x to the 2. And this one here, this is just because 9 times 9 factorial over 2 factorial equals to, 9 times 8 times 7 times 6 times 5 times 4 times 3, because there's an x2, so we have to cancel all those. Divided by 2 times 1. So this is going to be 2 times 1. So it cancels all those. So we're left with, just the, we have to cancel that out. That's why we have a 2 factorial at the bottom. Divide this by negative 7 factorial, and then x to the 0 or 1. And then like that, this can be minus dot, dot, dot. And also put this 756. Now the next one's going to be plus 13 over 756 times it by exactly the same thing. 9 factorial over 2 factorial. This will be x2, and it keeps going on and on. Then minus plus because alternating dot dot dot. And then when you plug in the 0, this goes to 0. Everything else goes to 0. This goes to 0. This goes to 0. So all we're left with is this over there. This equals to, this equals to negative 7 factorial over 30. Divide this by, I'll put this a bit neater. Let's put it over here at the bottom here. So this equals to 7 factorial over 30 divided by 7 factorial over 30. And in fact, when you calculate this out, this equals to, negative 168 over 168. So this is exactly what we get. So circle this out like that. Don't circle that until you get the answers. This equals to 1. And this is exactly the same thing as our solution or our question 3. So the calculation check, you go 7 factorial, it goes 5040, and you get negative 7 factorial divided by 30, we get this negative 168. So that's exactly this. So this result agrees with the result in question 3, which had the exact same one. So anyways, now let's look at question 5. So let's go read it. And also show over here earlier. So this is a negative 168. The 7th derivative gets exactly the same, which is fascinating stuff. It just shows you how mathematics is all tied together perfectly logically, so that you can use many different methods of getting the exact same answer. Anyways, let's keep going further. So example question 5 states, use the limit command on your CAS to find the limit as x approaches 0 of f(x) directly, and most computer algebra systems use the method of question 4 to compute limits. So yeah, most of them just use Taylor series and all of a sudden just take the limit, because it's pretty epic stuff. Because Taylor series just makes any random calculation, like for example sine, trigonometric ones, inverse functions, all into basic polynomials where you're just adding infinite terms of x to the power of something and then times a constant. So you make these all uniform and calculate it, which is quite amazing if you start to ponder it. So anyways, let's go to question 5, and you could again use amazing Wolfram alpha. Just calculate that. So let's go to Wolfram alpha, and it's a solution to question 5. So if we calculate, if we calculate the limit directly using Wolfram alpha, we get the correct answer. There's a link to it. So you could just literally just type limit of sine tan of x minus tan sine of x divided by a sine, or for inverse, a sine a tan of x minus a tan a tan of a sine of x, all brackets. Get the brackets all correct. As x approaches 0, you get limit as x approaches 0, and it automatically shows you in this format. Sine tan of x minus tan sine of x, etc. Inverse sine of inverse tan of x minus inverse tan of inverse sine of x, all brackets, equals 1. Fascinating stuff. So now a solution to question 6. Let's look at that. Question 6. Question 6 asks, let's scroll up here, a lot of scrolling back and forth. And so in view of the answers to questions 4 and 5, how do you explain the results in questions 1 and 2? Remember, questions 1 and 2, they had digits of precision were 10 to 15 or 17, and they were giving the wrong answers. So getting 0, we got 10 over 3 on this one. The other one we got undefined. So now it's asking, how do we come to terms with that? So what's our explanation for why the answers in the question 4 and 5 gave 1? Yes, questions 4 and 5 gave 1, as well as 3 gave a equals to 1, but how do you explain the results in question 1 and 2? And yeah, because we were using the same CAS, the same Wolfram alpha to solve it. Yeah, actually, I didn't actually use the Wolfram alpha. I used the Desmos, Maple, and the Excel, or the Maple from the Solutions Manual. But if you go to Wolfram alpha and you get this giant formula, sine tan, and then plug in 0.001, and then minus tan sine, and then 0.001. Even Wolfram alpha gives you the results undefined. So even this one's undefined. So yes, fascinating stuff. So that would be undefined, just for reference, to show that I had that included. But anyways, let's keep going further. And now let's explain away what this would mean. So the strange results with only 10 to 17 digits of precision from questions 1 and 2 must be due to the fact that the terms being subtracted in the numerator and the denominator, because remember there's a subtraction there, are very close in value when absolute value of x is small. Thus the differences are imprecise, have a few correct digits. We can see this is the case by comparing the graphs of the terms in the numerator as well as comparing the terms in the denominator. And when we zoom in near x equals 0, we see that the values of the terms are almost identical to any level of zoom we get. So if we graph sine 10 like this and you zoom in, they're almost identical. This is 10 to the negative 18. This is beyond the precision of the earlier calculators. And then going further, so if you do the same thing for the denominator, so inverse sine of x, inverse sine of inverse tan of x, and then the inverse tan of inverse sine of x, we get the same thing. You graph those ones together, it looks absolutely identical. And you zoom in, it's very, very close, even at the 10 to the negative 18, so the 18 digits precision, or the 18 digit zoom. And then even if you do it for each terms, even the ones inside, so sine of x, tan of x, inverse sine of x, inverse tan of x, so the graphs all look like this. So remember the graphs that we had earlier drawn. So this is the red one is the vertical red one is the tan of x. Yeah, so it has a period, keeps going on and on. It's periodicity. In other words, just repeats. And then then a dash red line is the inverse tan of x, goes like that. And again, they're all very, very similar at x equals 0. And then we have the black one is the sine of x, dash black one is the inverse sine of x, exactly like our graph. And then if you zoom into the 10 to the negative 18, we get exactly all of them look exactly the same. Thus, the terms themselves are near identical when zooming in beyond even the level of precision of most calculators. To illustrate what this means, consider the following calculations of 10 digits of precision. So if you have division, here's the exact calculation, but let's say you only have 10 digits precision. And so this is, let's see, that's 10. This can be, so including the 0 there, it's going to be 5. And then 1, 2, 3, 4, 5, so that's 10. And then beyond that is 279, we have this 111. So 1, 2, 3, 4, 5, and then 279, 111. Subtract that, we get, divide these out. So if we divide for division, we get 1.00013608626. So division is all right. You get pretty much 1 with 4 zeros there, a lot of zeros. And then if you do the calculator with 10 digits of precision, these are cut out. 279, 111 are cut out. So we get this 0.0001234 divided by, we get 1. So we get 1, which is still close to this answer. Yeah, so it's still very close, 1 and 0.0001. But then when you do a difference, we get the exact one here is the exact same thing, but we're subtracting. We get 000 all the way to 168. So 279 minus 111, the only thing different. So we subtract this 1, so 1688. And then we get this one, and this also this calculator is used, the Google calculator. So anyways, so that's the exact 0.0000168. But then if you do the calculator, we get this 1, 2, 3, 4, 5. These cut out these endpoints. These last terms. So we get 1, 2, 3, 4, 5 subtracted by 1, 2, 3, 4, 5. We get 0.0000. And dividing differences that are rounded to 0 is undefined. You get the indeterminate form of 0 over 0. So that's why even Wolfram Alpha gets you a 0 over 0. And that's why they get undefined over there. It's fascinating stuff there. So hashtag interesting stuff. So yes, that is all for today. And let's just scroll up. And I made this video all in one go, actually. It's the first time in a while I usually have to cut, pause, and then fix some stuff up. Hopefully I don't have to do that. Anyways, that is all for today. Hopefully you'll learn. And like always, you can download these exact notes in a link in the description below, as well as viewing these notes on the Hive blockchain, link in the description. Anyways, thanks for watching, and stay tuned for another Math Easy solution.